Hello everyone, welcome back to this course on reinforced concrete design. We are in week 4 and this is our first lecture. In this week, we are going to learn column design. So, let us first define a column and then step by step we will see how we can design a column as per Indian codal provisions. So, it is a member, a structural member having compressive load. Now, when we say column, we always mention a vertical member, right? Of course, it can be inclined also, but let us for the time being not consider any other orientation. So, we will talk about a vertical structural member that is going to experience an axial load causing compression. Now, the cross section of the column can be of different type. It may be rectangle, then square, then circle, and obviously there are different other geometries also available. For the time being, let us focus on rectangular column only. Of course, we will also talk about circular columns. Now, for a column, because the member is in compression, the material that we use, concrete, it is also very good in compression. Right. Now the question is, even if we have concrete which is good in compression, we provide rebars. We'll see the orientation of rebar in a minute, but at least one thing is for sure, we should provide these rebars at least minimum quantity. And of course, if you go beyond minimum quantity, it is also provide excellent resistance against compression. Right. So, the cross section of a column, for the time being, let us consider a rectangle, and that rectangular column is made of concrete with certain grade, and it also has some rebars. Now, when we talk about rebars, as I have already mentioned, that there must be a minimum quantity present for a particular cross section. There is also a maximum limit. For a given cross section. One by one we will study what are their values and how we can actually design a column against a compressive load and find out the requirement for steel and concrete. Now, we have two types of rebar in a column. One is obviously the longitudinal and transverse. Now, in this course, we'll design RCC column, but remember, there may be composite columns as well. We are not going to study any composite column and their design. So, our objective is to go for a regular section like rectangle, square or circle, where we'll have concrete and rebars in both longitudinal direction and transverse direction. Now, when we talk about transverse reinforcement, we can have ties or spirals, okay? But in this course, we will only talk about ties. So let us first see the cross section of a column, and then we'll study what are the different requirements. Let this be the cross section of a column. And if I draw the side view, then we get this type of arrangement. Now, inside we have rebars. So, we have rebars at the corners. And if we see them in side view, these are the rebars. And then there are lateral ties. So, this is the basic arrangement of rebars in a column. So, our task is to design this diameter of this column. It is made of some grade of concrete. There is again here clear cover on either direction. And then we have this centroidal axis. So, if we draw the centroidal axis, which is along this line, now, as you can see, we assume the load is acting at this center point. The point to be noted here, if you look at the arrangement of steels, they are symmetric. Okay. We will not design a column with a symmetric steel arrangement. Okay. Now, there are certain assumptions. Let us write down the assumptions and then gradually we will move over to the design of column. So, assumptions. The first assumption is plane section perpendicular to the axis of column remains plane after deformation. Second assumption, uniform strain and stress distribution for concrete. And the maximum strain, so the strain in concrete is 0.002. Now, if you recall, earlier we discussed for this concrete, FCK is the value of concrete strength. We have defined this earlier. Now, we get this FCK from the cube test, and therefore stress level stress in concrete is 0.67 FCK, as we did in case of beam design, and then factor 1.5. So ultimately we will get 0.446 FCK. So that is for concrete. Now for steel, we have Fy as the yield stress, and we have gamma material factor for steel is 1.15. Now, let us first draw the cross section of this once more, and then what we'll do, first study the strain distribution over concrete. So this is uniform. So we have, this is our strain distribution. And then stress distribution also, let us see. So the stress distribution and strain distribution are shown here, which is uniform. So this value is 0.002. So this is strain in concrete. Because we apply the load at the center, it acts uniformly over the entire cross section and we get a uniform strain. And for stress, this is 0.446 FCK. Stress in concrete. Now, once we design a column, so the side view of the column, as you can see, it has a length which is shown here. Now, as per IS 456, we can find out the L effective. Okay, so if you have a column which is spanning between two floors, so it is the distance between the soffit of the beam to the floor level is basically the height of the column, and then L effective is the height of the column that we can define along x direction, as well as we can have a different value along y direction. So if this is D and this is B, then L by D ratio, if it is less than 12, then we call it short column. For the timing, let us consider short column, and this ratio we have to check for either directions. And for effective length, it depends upon the boundary condition also, as you all know. So, for different boundary condition, the value of the effective length changes. We'll see that in a minute. But for this cross section, first thing to be noted here is the sectional capacity. So for design, we have sectional capacity PU, that is the ultimate load carrying capacity. It will have contribution from concrete and steel. Now for concrete, the design stress is Fc times the cross-sectional area of the concrete is the force resisted by the concrete section. Similarly, we have for steel Fs, that is the design stress times As. Now we already know the value of Fc, which is 0.446 FCK times AC. Plus, for steel we know it is 0.87 because we have defined the material factor times Fy times As. So, the load carrying capacity, ultimate load carrying capacity of the column is shown here, as you can see. So, this is equation number 1. Now, for a given cross section where we know B and D, we can actually first check whether it is a short column or not. For the timing, let us assume that it is short column. Then for that short column, we can easily find out the sectional capacity using this equation 1. Now, as you can see here, we can write this sectional capacity Pu in this compact form. So we have alpha C times FCK times AC plus alpha S times Fy times As. So that is the sectional capacity of the column, to be more precise, short column under axial loading. So what is the value of alpha C? This is 0.446. And for different grades of steel, we have different values of alpha S. So alpha S for Fe250, it is 0.87. Fe415, it is 0.79, and 500, it is 0.75. Now for simplicity, IS code says that let us use alpha S is equal to 0.87. So for all different grades of steel, we will use this value, and our Pu will be contributed by concrete as well as steel, that we have already derived. Now for short column, if you have, this is the cross section, as you can see, we have applied the load which is exactly at the center. So here we have the loading. Now in reality, it is difficult to apply that load exactly at the center. Sometimes we have a minimum value of eccentricity. So instead of this point, we apply the load here, and therefore we have eccentricity along both the axes. So this is, say, the eccentricity. And for the time being, let us just consider, say, Ex, and similarly we have Ey. Let us talk about eccentricity along X. Now, because of this eccentricity, you can easily sense that in addition to the axial compression, we'll also have a moment. If the load is applied here, it will apply a moment about this centroidal axis, which is the load, maybe say P times the eccentricity. Now, when we design a column, first we will learn how to design this column against an axial load, but even for that, we will design it for a minimum value of eccentricity. So, the minimum value of eccentricity as per IS 456/2000, clause number 25.4, E min is equal to L by 500 plus D by 30, subjected to a minimum of 20 millimeter. Now, you can see we can fix this length of the column, then also the dimension. From there, we can estimate the minimum value of eccentricity for the column, even though we, for the time being, consider only axial compression and no bending. We will gradually see how we can consider bending in one direction, and then we will go to biaxial bending. Now, there is another clause, clause 39.3. It says if E minimum is less than 0.05 D, then the design of short column is using the following expression. So, Pu is equal to 0.4 FCK times AC plus 0.67 Fy times AS. So, this is equation number 2. I repeat once more, if the E minimum is less than 0.05 times D, then we can modify the expression in equation 1. As you can see here, equation 1 is modified to this new formula that is in equation 2. Now, here one thing to be noted, as you can see, we have 0.05 D is greater than the minimum amount of eccentricity that we design, and if you use this expression, what we can conclude that D must be greater than equal to 400 millimeter. Again, what we have E minimum is equal to L by 500 plus D by 30, which is following this relation. So what we effectively get is L by 500 should not be greater than D by 20 minus D by 30. Or in other words, it should not be greater than D by 60. That is, D should be less than 0.12 L. Recall, in our beam design, we always started with a cross section to deal with the deflection. Here also, when we design a column, first we check the effective length of the column, and based on that, we first decide what should be the dimension of the column, and then once that is satisfied for this minimum eccentricity, then we can design the column. Now, let us revisit equation 2. Pu is equal to 0.4 FCK times AC plus 0.67 Fy times As. Now, we all know that the percentage steel PT is nothing but As divided by Ag times 100, right? So effectively we get As is equal to PT times Ag divided by 100. So if we modify this expression, what we get 0.4 FCK, then we have Ag. Ag is the cross-sectional area of the column. So if this is the cross-sectional area, we have D by say B. So Ag, that is the gross cross-sectional area, is B times D. So what we have here, Ag minus the still As, the expression of As is here, so it is Pt times Ag divided by 100 plus 0.67 Fy times Pt times Ag divided by 100. Now, if you look at this expression, what we have on the left hand side is the ultimate load carrying capacity. That ultimate load carrying capacity depends on what? The type of concrete we use, the type of steel we use, and the percentage of steel. So effectively we can rewrite this expression. So we can write Pu ultimate divided by Ag is equal to 0.4 FCK times 1 minus Pt by 100 plus 0.67 Fy times Pt by 100. So you can see for different values of FCK and Fy, and of course percentage steel, we can have design curves, right? And if you plot this Pt versus Pu by Ag, we get a straight line. For a given combination of FCK and FOA. And these design charts, so these are the design charts or plots. These type of design charts are available, and for that we have another codal provision that is called SP16 1980. This is the design aids for reinforced concrete to IS 456. So we have another guideline SP16 where we get this type of design charts, and from that chart directly we can read these values of PU by AG for a given percentage of steel. And because we already set AG, that is the gross cross-sectional area, we can easily evaluate the ultimate load carrying capacity. And these design charts are available for different grades, different percentage of steel. And also, if you recall, we started with this equation 2, right? Instead of equation 2, we can also derive the same expression or similar expression for equation 1 also. So it gives clear idea about how to get the ultimate load carrying capacity of a given cross section when we set the FCK value and FY value. Now, either we can start with the design value of the ultimate load and find out PT, or we can propose a PT and then we cross verify whether the sectional capacity we have is sufficient enough to withstand the design. So from our structural analysis, we have a demand. So what we do, we set this PT values, and then for a given cross section, we find out what is the capacity. If that capacity is more than the demand, our design is okay. Or we start with the demand and that load we fit in to this design charts to find out how much steel we need. Now, when we talk about longitudinal steel, as I told you earlier, there are certain minimum and maximum requirements. So let us quickly go through those guidelines. So longitudinal steel in column. So the first requirement is it should not be less than 0.8% nor more than 6% of the gross cross section. Now for any column, normally we prefer to limit ourselves within 4%. So we do not go beyond 4% because then within a section we will not have sufficient spacing between the two longitudinal rebars, and that causes trouble in compaction, because unless we have good compactions during constructions, then honeycomb is formed and that doesn't offer the strength. So if we have too much of steel, then that occupies a large part of the cross section and it is then not surrounded sufficiently by the concrete. And if there is improper bonding between the concrete and steel, obviously we will not get the desired strength. So from the construction point of view, we always set this 4% limit for column. We do not go beyond 4%, although code specifies that we can go up to 6%. Now, For a column having larger cross section than required, then PT percentage steel must be based on AC. Now for a column cross section, there must be minimum number of bars, which is 4 for rectangular cross section and 6 for circular cross section. Finally, the diameter of the bar, so the minimum diameter of the bar in longitudinal steel is 12 millimeter. So these are the codal provisions that we have, and in design we must satisfy all these requirements. Quickly, if I summarize, the diameter, minimum diameter 12 millimeter, then 4 number of bars at least we should have for rectangular or circular cross section, square cross sections, and 6 for circular cross sections. Then we should not go beyond 4% of the steel. If there is a requirement for beyond 4%, we have to redesign the cross section. However, code says maximum limit of 6% and a minimum limit of 0.8%, right? Okay. Then, once we fix all these parameters, the spacing between longitudinal bars should not be more than 300 millimeter. Recall, in case of beam also we had this requirement for spacing. Here for column, 2 bars should not be more than 300 millimeter apart. So these are the longitudinal bars. As you can see, here we have 2 bars. So the distance between 2 bars should not be more than 300 millimeter. If we have distance more than 300, then we have to provide at least a minimum diameter bar here. So we have to redesign or readjust the amount of steel. So we can actually find out this amount of steel from the design. Then we select the bars. Remember, we have to select minimum 12 bars. And if we have by chance spacing more than 300, then we have to provide a minimum diameter bar in between. Now, beyond this, there are certain other guidelines for this minimum steel for pedestal and for helical reinforcement. But for the timing, we are not going for helical reinforcement. That we'll take it separately if the time permits. We have this horizontal ties, as you can see here. But remember, there are certain guidelines if you go for helical reinforcement and if we design a pedestal. So now we have to check this transverse steel, and for transverse steel also there are certain guidelines. So let us see how we design this transverse steel. So for that, let us draw the cross section once more, and then we'll see the requirements for transverse steel. Okay, so we have transverse steel here. Now for this transverse steel, okay, so if we have longitudinal steel with spacing less than 75 millimeter, then for this case, so longitudinal spacing, longitudinal rebar spacing is not more than 75 millimeter, then we need only transverse reinforcement to go around the corners and alternate bars for effective lateral support. What does it mean? It means if we have, this is the arrangement as you can show here, then what we'll do, we'll put alternate bars, or let me just draw here. So we have one bar going all the way here and then take the corner, come here, then this bend here, and then they are anchored like this. Another bar will start from here, go all the way round this bar and to the extreme. So it will be like this, and at this corner it will be anchored, right? So that is the arrangement if we have the longitudinal spacing of rebars not more than 75 millimeter. Now, if we have a different case, so longitudinal rebars spacing is not greater than 48 phi, then additional longitudinal bars in between, they need to be tied, using open ties. So let us draw the arrangement and then it will be clear. So if you have this is the arrangement, and then we have these extremes, these bars, and this spacing is not more than 48 phi. Then we have these alternate bars, and for that we will have a tie here which will go around these bars. So that should be the arrangement of lateral ties. In addition to the one that is covering the entire loop, and they must be also anchored at the corner. Okay, so now let us see the minimum requirement of pitch and diameter for these lateral ties. So minimum requirement of pitch or spacing of this tie should not be more than minimum of a least lateral dimension be 16 times phi of smallest longitudinal bar and then C 300 millimeter. Recall in case of beam design, we had this requirement for stirrups. Now for this lateral ties, this is the requirement. So we have to estimate these three parameters and then minimum of that is the requirement for pitch of these lateral ties. Then next is for this lateral tie, dia should not be less than 1/4 of phi largest longitudinal bar and in no case less than 5 millimeter. So for lateral ties, minimum phi min is equal to 5 millimeter. So we can't go below this point. That comes from this. So first we have to find out 1/4 of the largest diameter of the longitudinal bars. If that value is less than 5, then we have to provide 5. Otherwise, we have to provide this value. Okay, so now the last thing before we take an example for the design is the L effective. As I told you, it depends on the different boundary conditions. So if we have fix, it is L by 2. If it is fix hinge, then it is L by root 2. If it is hinge, it is L. And there are other conditions also, but in IS 456, there is a dedicated table that modifies this value slightly, and then it gives basically the L effective for different boundary conditions. Nevertheless, the point to be noted here is that the L effective depends on the boundary condition. So if we have a slab here and then a floor here, and just imagine if there is a beam for this slab, and if we have a column, then first we find out from this soffit of the beam this clear height of the column, and then based on the boundary conditions here and there, we decide the effective length of the column. I repeat once more that these values are further modified, and that table is there in IS 456. When that example will come, we will show you. Right. Now with this background, let us quickly design a cross section and see what is the capacity for a rectangular column. So let us consider a rectangular column . Now the dimension of this column is 400 by 500. It has 425 bars. It's made of M30 concrete and Fe 415 bars. Our task is to find the capacity of the section. So what we see here, D minimum is equal to 400 millimeter, and recall this is okay for E minimum of 20 millimeter. Now let us first find out gross cross-sectional area. So that is 400 into 500, which is 20 into 10 to the power 4 millimeter square. We have FCK value is 30 Newton per millimeter square and Fy is equal to 415 Newton per millimeter square. Also, we know AS, in this case it is 4 times the diameter of a bar is 20 millimeters. So pi by 4 times 20 square, we get 1256 millimeter square. So AC is equal to AG minus AS. So that value is 1,98,744 millimeter square. So PU is equal to 0.446 FCK times AC plus 0. Let us use the exact number of alpha S. If you recall, for different values of still, the value of alpha S changes. So let us use this exact value, which is 0.79, although we can use 0.87 as per codal provision, into Fy times As. So if we put all these values, we have 0.446 times FCK 30 times AC 198,744 plus 0.79 times 415 times 1256. So this is equal to 3071 kilonewton. So now we can find out allowable service load. So P allowable is equal to PU divided by the factor, which is say 1.5. So we have 3071 divided by 1.5. So we have 2047 kilonewton. So for the given cross section, here you can see we have estimated the allowable service load. So with that, you get the idea of different design steps for axially loaded column and the different provisions given in IS 456. So let us stop here. You go through these details, and in the next class we'll solve some example and we'll see step by step how we design a column and how we also develop the structural detailing. So that will be in the next class. If you have any doubt, do let us know and then we will clear your doubts. Thank you very much.